What if the key to controlling magnetism doesn't require heavy metals at all? For decades, researchers have relied on materials with strong spin-orbit coupling like platinum and tungsten to generate the torques needed for magnetic switching, but this work reveals that light metals like titanium and niobium can produce comparable effects through an entirely different mechanism. Let's start by understanding why this discovery matters so much for the field of spintronics. Building on this challenge, conventional magnetic control has been bottlenecked by the need for expensive heavy metals. The authors recognized that orbital angular momentum currents, predicted to exist even in weak spin-orbit materials, remained largely unproven experimentally. Now let's explore the key physics behind their breakthrough approach. The elegance of this mechanism lies in its two-step process. Unlike traditional approaches where the same heavy metal generates and delivers the torque, here the light metal generates orbital current that gets converted to useful spin torque only after entering the ferromagnetic layer. This comparison reveals why the orbital approach opens new possibilities. The authors hypothesized that the ferromagnet choice would be crucial, since orbital to spin conversion happens within that layer rather than in the current-generating metal. To test this hypothesis, they designed carefully controlled bilayer experiments. The device fabrication required precise control to ensure clean interfaces between the light metal and ferromagnetic layers. They systematically compared 4 different bilayer combinations to isolate the effects of each material choice. The second harmonic technique is crucial because it separates current-induced effects from equilibrium magnetization signals. By analyzing how these voltages depend on magnetic field angle, they could extract the strength of orbital-induced torques. Their measurements revealed striking differences between the ferromagnetic materials. These results provide compelling evidence that nickel acts as a much more efficient converter of orbital angular momentum to spin torque compared to nickel iron. This ferromagnet dependence strongly supports the orbital Hall mechanism, since conventional spin Hall effects shouldn't show such dramatic material sensitivity. The control experiments were crucial for validating their interpretation. Without the light metal layer to generate orbital currents, the ferromagnetic films alone produced no detectable torque or resistance effects, confirming that the bilayer interface is essential. The unidirectional magnetor resistance measurements provided independent confirmation of orbital current effects. This resistance phenomenon, where electrical resistance depends on both current and magnetization direction, showed the same material trends as the torque measurements. Let's examine some of the more subtle technical discoveries that emerged from their analysis. Interestingly, the different light metals showed distinct signatures that helped the authors separate orbital effects from conventional spin currents. Niobium, having slightly stronger spin-orbit coupling than titanium, produced some additional spin current contributions that were detectable in their measurements. A key challenge in bilayer experiments is determining how much current flows through each layer. The authors used careful resistivity measurements and circuit modeling to quantify the current density in the light metal layer, enabling them to calculate meaningful torque efficiencies. These findings opened several important new directions for magnetic device engineering. From a practical standpoint, this work suggests that magnetic memory and logic devices could potentially use much more abundant and cost-effective materials. The discovery that ferromagnet choice is critical also opens new optimization strategies that were previously unexplored. Beyond the immediate technological implications, this research establishes orbital angular momentum as a legitimate and measurable quantity in solid-state devices. The work bridges theoretical predictions about orbital currents with practical device measurements for the first time. Like any pioneering work, this study also reveals new questions and technical challenges. The authors had to develop sophisticated analysis techniques to separate orbital effects from thermal artifacts and other competing mechanisms. The complex angular dependencies of their signals required careful modeling to extract meaningful physical parameters. Moving forward, researchers will likely explore other ferromagnetic materials that might be even better orbital-to-spin converters than nickel. Interface engineering and device optimization represent rich areas for continued investigation in this emerging field. This work fundamentally expands our toolkit for magnetic control by demonstrating that orbital angular momentum transport can produce measurable effects even in materials with weak spin-orbit coupling. The key insight that ferromagnet choice determines conversion efficiency opens an entirely new dimension for optimizing spintronic devices, suggesting we may have only scratched the surface of what orbital currents can achieve. Visit emergentmind.com to explore more cutting-edge research in quantum materials and spin